a project that I kind of started and completed at the end of 2019 down in Willesden. So we're going to have a chat about the removal of 2 gantry cranes on the site using a large crawler crane, the actual movement of gantry crane B that was done over a Christmas possession using a number of SPMTs to move the crane, and then the actual pull down of the gantry crane. I've got some nice videos and things to keep everyone entertained. So to give you a bit of an overview of the site, so I've labelled all the gantry cranes. This is Willesden down in London. So I'll just get the pointer out. So gantry crane B, which is the one that was pulled down, is this one over here. C and D are these ones. These were lifted off with a large crawler crane and dismantled in sections. So these lines here, so just to the north of gantry crane B and A, are live network rail lines out of Euston. So obviously there was a high amount of risk involved. If anything went wrong, it would have been pretty serious, and we were definitely aiming to avoid that. So just to give you a bit of the HS2 spiel, so this is going to be used for the tunnelling works and as a logistics depot for all of that. They've claimed that it's going to take around 300,000 HGVs off the road of London, and kind of, I think it was handle about 6 million tonnes of excavated material. So it's going to be quite an interesting project when it gets going, and I'm glad it's going ahead. Otherwise this presentation would feel a bit more wasted. So the first thing I'm going to talk about is the removal of gantry cranes C and D. So this was done with a big crawler crane that came onto site, and it was positioned on areas of both hardstanding and some areas where the hardstanding had been removed by the previous demolition works. So we designed some outrigger pads. Obviously the loads were pretty considerable, just over 2,000 kilonewtons. So we used a kind of a combination of a working platform which was tested with plate bearing tests, with Eki mats, and then the proprietary crane mats that came with the crane. These kind of spread the loads down to an acceptable or an allowable bearing pressure, and kind of kept the deflection to the minimum. So I'm just going to go over a bit of the actual lifting. So it's just a drawing we did, just showing the kind of the outline areas where they were lifting, and more importantly, from our point of view, the outrigger locations and the testing requirements. So each of the cranes was lifted round between 90 and 270 degrees in sections. The picture at the top shows the actual construction of the crane. So it is formed of both a turntable that was sat on a square steel frame with 4 legs that came down, all with moment connections, quite a stiff frame, which is quite different to gantry crane B, as we'll see further down. So I've robbed a video off YouTube of the actual demolition of these. So this is from HS2. This one doesn't have sound, so it shouldn't be deafening you. It just shows the setup of the crawler crane and then the demolition methodology. So I think Sarans and Hunts, our client, get a good show in here parking their excavators in front of the camera. One of the things here was that because we were demolishing both cranes, we actually had a look at some of the services in between, and we found that unfortunately we couldn't drive the crane while fully loaded between the two. So there was the requirement to de-rig and dismantle between each set of lifts. As you can see, they kind of removed the turntable first and then pulled the crane over and then cut down the legs until it could be demolished more traditionally. And then that's that. So moving on to gantry crane B, so this is the one up next to the network rail lines. Part of the scope of this was ALE were brought in to move the crane using SPMTs, which are the self-propelled modular transports, the big flatbeds with about 8 wheels each. And what they were doing was they were moving it off the rail lines and then onto this existing hardstanding to the south. And they also turned it 90 degrees so that when we did pull the crane down, we were pulling it parallel to the lines So there was no risk of it actually falling onto the network rail assets, and it was outside the fall radius. So to do this, the green area is obviously an area of railway tracks used by the old trains that came into the Euro terminal, and there were still live rail operations once a week while we were on site. So we had to ensure that our existing our new hardstanding that we put in had all the flangeway clearances, and the trains could operate during all of our works there. So this was our proposal, and this is what was put in. We had to kind of both make sure the trains could operate and ensure that these were removable, as HS2 didn't quite know exactly what they were going to do with the site after we'd removed the cranes. So we installed some lifting eyes, made sure it didn't cast into the chairs, and kind of made them fully removable. And when we moved the crane, we actually had to make some temporary foundations to sit it on. So these were built into the existing hardstanding. We created an opening and an excavation, and then cast these T-shaped foundations in. They had a little rail inset into them and some end stops. These end stops were kind of an SHS section that was cast into the foundation. And we then, after the crane was moved, you could drop a little UC section in there and pack it tight so the crane was not going to be moving once it was in place. And it was definitely then, it definitely wasn't moving during the actual demolition process. And we just produced this reinforcement drawing just to show them exactly what we were looking for. So onto the actual pull down, what I'm going to have a chat about is the temporary stability of the crane, what we considered loading wise, and then the destabilizing load, how we kind of designed out the risks to the operatives during the pull down process, and then a little bit on some of the lessons I learned from the project. And there's a nice video in there as well. So this drawing just showed our kind of pull down sequence. This was completed at tender stage originally and then was continually up revved. So we were, bring the pointer along. So the cuts were made just here at the top of the legs, the blue line, with an excavator, with a backup excavator there to provide the pulling force. And then we had engineered fill mats to reduce any vibration and to kind of avoid any flying objects. These were formed of like reused material from the site to demolish a few other buildings. So this was all graded and engineered fill and then was used for these, and to form some other granular mats over the rail lines to allow the SPMTs to come into position. So, and then we showed a kind of a collapse sequence, which was surprisingly enough followed. And the video shows it does actually come down like that. So this shows the cutting sequence. So the legs are made up of these box sections. You've got the webs here, and then the outside flanges. Well, that is the inside flange, and that's the outside flange there. So how we progressed these cuts was the inside flange we cut first. This was the hardest to get to because you had to get the nuke up inside the leg. And then we progressed by forming some inspection holes and removing the diaphragms. I'll talk about that a bit more in the lessons learned, because in fact those diaphragms didn't actually exist. We then provided the shim shown green here. So we cut in and we put in some equal angles to take the compressive stress that would be there, and there were 4 tabs left here along the beam, and these were to be broken finally when we did the pull down. So that was the stage 1 cuts there. We did this to each leg, working round sequentially, and then the stage 2 cut and final cut here is on the outside face of the leg. This is to design out the risks to the operative, so he could make this cut while being outside of the fall path of the crane. So if there was a gust of wind or any other unknown impact on the crane that caused it to collapse prematurely, the operative would not be in the fall path. And though I'm sure he would not have been happy, he would have been safe. Just to draw some attention down here, so we'd specified a wind speed of 8 meters per second for these final cuts. So on the day of the actual pull down, we had a lovely calm day in the end, which was good. But yeah, we'd specified a maximum wind speed that the crane could take, and this was calculated looking at the area on the windward faces and kind of balancing that out with the pulling force required, so that we cut just enough and had the tabs left to resist this wind load, but would be they would fail in yielding when the actual pulling force was applied by the excavator. So this is just a picture. So as you can see up at the top here, the front legs had been fully cut through at this point. There was only the 4 tabs and the hinge on the back side that was still there, and the operative is in the mute, commencing the final cuts. I think it's perspective that makes him look in the full path. He is actually back from the leg and out of the way there. But this just shows that as the crane falls to the left, he would not be kind of in any danger there, though definitely unhappy if it came down. This is just a video of the actual pull down, just to show the process. I've turned the volume down, so hopefully it doesn't deafen you. You can just see the chain and the wire coming tight there from the excavator, and the pull down is initiated like that. So that shows that process. It did come down very smoothly, perfectly onto the actual fill piles, and there were no issues in the end. It was a lovely day. So on to lessons learned. So as I previously mentioned, we'd drawn up internal diaphragms on the beams. It was a structural report which showed them. I've just taken an extract from it here that's kind of indicated there were internal diaphragms, and you can kind of see it on the picture, the actual diaphragms. When we did our first inspection cut on the when we were carrying out the stage 1 cuts, we found those didn't actually exist, and what was on the inside of the legs were internal, or some equal angles welded to the inside of the legs. So it wasn't just on these 2 webs, there was some on the internal and external flanges as well. So lessons learned, it wouldn't have taken much to put some inspection holes in to confirm the existence or non-existence of the diaphragms, and we could have then sequenced our cuts a bit differently to make it a bit easier to cut them out. In the end, the burner could just about reach the equal angles on the inside of the flanges, but it wasn't the best situation. So even when you think it's obvious what's inside there, you've got all the reports, it's always worth double checking on site, because it didn't catch us out too much in the end, but there was, it could have gone a bit, it could have caused us some issues with the actual pull down sequence. So, and I think